And I already mentioned several times that there's something which we call Monte Carlo modeling. And so I tried to explain a little bit what that means. In principle, it's a straightforward technique. What you see here is on the left-hand side, typical scenery we use for our Monte Carlo code. So we have a domain, which is a cube, basically, or a cuboid, whatever it is. So in this case, plane parallel, you can make it spherical as well at the ground. And this volume element can contain a number of things, clouds and aerosols and molecules, of course, which can scatter and absorb radiation. And what we do is we trace individual photons through this scene. What that basically means is you start a photon at the top of atmosphere, then it might hit a cloud, and then it's maybe scattered to this cloud and scattered again until it reaches the ground. And if you do this with one photon, you don't learn a lot because it might reach the ground or not. I mean, if it reaches the ground, you could see, say, 100% of the photon reached the ground, so the transmission is 1. But of course, to make a meaningful assessment of the real transmission, you need to trace many photons. As many as possible, and the more the better. Well, as many as possible basically means you need an infinite amount of computational time, but it depends a little bit on your accuracy requirements. So if you require 10% accuracy, this can be very fast. If you require 1%, it takes a little bit longer. And the higher your requirements concerning the noise, I should say, actually, it's not the absolute accuracy, it's the noise. The lower or the higher the expectations, the longer the computational time. And it will never be noise-free, of course. So this is our model, and this is what it can do. You see a similarly cloud here. So on the left upper here, we have a distribution of liquid water and ice water with an assumption about the droplet sizes, and you have profiles of everything. So 3-dimensional distribution. So this is in X and Y and Z. Where do you get this data from? In principle, you could get them from observations, but I guess those of you doing remote sensing know, well, cloud remote sensing, you never get a full picture of the cloud. You would need a fast scanning radar, which detects all the pixels, all the droplets, not just the big ones, but also the tiny ones. Extends up to 10 kilometers, which is not difficult for a radar, has high resolution and everything. And then you just have a radar reflectivity, but to derive liquid water content from that, you need assumptions, whatever. So the most complete picture comes from a cloud resolving model. So this is a numerical model which can predict atmospheric movements and the formation of droplets. And well, every numerical weather prediction model can do that. You maybe want higher resolution, and there's models like the WRF model or whatever it is to produce this. And then you can use it as input to the Monte Carlo code and calculate radiances, and that's what's displayed here and here. So we're looking straight down at the cloud from high above, from aircraft or from the satellite. And this is what the cloud would look like. And if you have an inclined angle, let's say 60 degrees from the side or so, the cloud would look like this. It's pretty cloud-like, I would say. Now, there's some stuff missing. If you really look down at the cloud, you will probably notice they never look that sharp down here because there's an aerosol layer, which is missing here in the simulation. We could have added it, but we didn't for some reason. Okay, and this is more realistic simulations. So we had a real high resolution cloud resolving model, which even produced some precipitation. So we see the clouds here seen from the ground. You see the ground, you see some precipitation. That's, by the way, also one of the nice things you can do with LibRadTran. You can actually calculate pictures. You can do that yourself. I mean, in order to calculate a picture, you need to calculate the full visible spectrum from 380 to 780 nanometers, and then multiply or convolve with the sensitivity of the eye for red, green, and blue, and then do some processing because the monitor usually cannot display all the colors which our eye can display, and then you get a color map in red, green, blue. But this can be done internally in Libratron. If you specify as an output option RGB, red, green, blue, you can directly get this picture. So this is ray tracing. In principle, you can make movies with that. So, you know, beginning from Star Wars, movies were made with ray tracing techniques, and nowadays you can't do any movie without, I guess. Not any action movie without, because for the dangerous scenes you always need some ray tracing and rendering. You can do it with Mystic, it's just very expensive because it's not optimized for making nice looking images, but it's optimized for being accurate. And the word Mystic stands for Monte Carlo code for the physically correct. That's the Y, physically correct tracing of photons in cloudy atmospheres. So we claim we don't do any assumptions, any simplifying assumptions, and we get the result as good as it is. Well, if you use the wrong equation, you get the wrong result, of course, but if you use the full radiative transfer equation with polarization and everything and the spherical geometry, then you probably get the result as accurate as you can get it if the input conditions are right. Good. Yeah, this is just an example. You can also calculate distribution of solar and thermal heating rates. And yeah, so this is the start of the simulation. And what I want to use the next 10 minutes is basically to show you what you can do with the model. By the way, I didn't check the time. When did I start? 10 minutes ago. So I have something like less than 15 minutes. Okay, good. So what do? We trace photons, and where do we start? Well, it depends on if it's solar calculation. When it's a solar calculation, you start somewhere at top of atmosphere, well, top of our domain. Not at the sun, because the first 150 million kilometers are pretty boring. It's empty space, but you start at the place where the atmosphere essentially starts at around 100 kilometers. And if it's the sun, you enter along the solar Venice and Artemis angles. If it's thermal emission, then you don't start at top of atmosphere, but at some place in the atmosphere. And you have to make sure that the number of photons emitted by a certain layer is proportional to the emissivity times the Planck function. So this is what we discussed this morning. And yeah, then you start walking into the atmosphere, and the first question is, of course, how far? How far do you go? And this is the most important process within a Monte Carlo model. You have a probability distribution, and you have to sample from this probability distribution. The probability distribution for the step width is essentially Lambert-Beer's law again, because that tells you how many photons survive after a certain distance. You could say distance, so then you need to calculate the probability with extinction coefficient times distance. The exponential of that is the survival probability. You can also think in optical thickness. That's much easier. So if you think in optical thickness, it's just exponential of minus tau, the survival probability. And since we have to save some time, I can't go into the details. If you think about it, you find out how you can do this, how you can sample randomly from every random distribution you can think of. We have many of them. It's not just how far the photon jumps, it's also the new direction after scattering. It's if a photon is reflected, if a photon is absorbed, if it's reflected at the surface, it's the new direction. So you have many, many probability distributions, and some of them are really complex, like a phase function. I mean, you have this strong forward peak, and you might have a backscatter glory and this sideward lobes and whatever. And you have to sample from that. But this is a very simple process involving the cumulative probability distribution. So we can do that. The idea is if you have a certain probability distribution and you sample from it, you get one random number. So if you sample a distance, you get something like tau equal to 2 or so. You do it again, you would get tau equal to 0.8, so random number, whatever. And you just have to make sure that when you plot the frequency distribution of your taus afterwards, that it equals the probability distribution. Okay, this is what I wanted to show here, yeah. So this is the probability for survival of the photon. And well, it basically comes down to the fact that the average distance between two scatterings is, how big is it in optical distance units? Yeah. Yeah. Optical thickness. Yes. Huh? Yeah. Mhm. It's 1. Yeah. So if you calculate the average optical thickness a photon is jumping, it's 1. That's the mean free photon path expressed in optical distance units or optical thickness units is 1. Mhm. Yeah. Yeah. But that doesn't mean that there aren't some which are scattered after 0.1 or 0.01, and some might travel 10 or so. It's just very unlikely. So, but you get this distribution. And then this is important that you get good random numbers, by the way. And yeah, you jump somewhere in optical distance unit, and then the next important step is to translate this to the grid again. Because you have a grid here with different extinction and scattering coefficients in each grid box. And this is actually a time-consuming process because you have to go through all the grid boxes here and count extinction times. Step width within this grid box gives you the optical thickness in this grid box, and then you add up all the optical thickness until you arrive at a certain point. So this is really tracing through all the grid boxes, and this is costs some time. But for standard forward Monte Carlo modeling, it's the most costly process here. Okay, so there's more about that. We found a new location. So we arrived here, somewhere in the atmosphere, and now the decision is what's going on here. Is it scattering? Is it absorption? Now, depending on if you use the extinction coefficient or the scattering coefficient, that can be different. But anyway, let's assume it's a scattering. And then you have to look into your particular grid box, what might be scattering. I mean, if it's cloudless, aerosol-free grid box, it can only be Rayleigh scattering. If it's a cloudy grid box, it can be Rayleigh scattering or cloud scattering. If you have aerosol, it might also be aerosol scattering. So you can decide what it is, again, depending on the contribution to the extinction. If you have a large contribution by clouds, then it's most likely clouds with some likelihood for Rayleigh. If you have more aerosols, then it's most likely aerosols, but it can be anything. So you have to sample again from the distribution at this point. And then once you decided, here we have different choices, molecular, aerosol, whatever. Once you decided what it is, you have to decide on a new direction, and you know the directional probability. So if it's Rayleigh scattering, it's quite boring. Phase function looks like this. And you can analytically calculate actually the probability or the angle, a random angle. While for more complex phase functions, like the me phase function here with a strong forward scattering peak, remember we don't plot as a function of angle, but cosine of angle here. -1 is backward, +1 is forward, and here's the rainbow. It's the forward scattering peak. If you translate this to a picture, it looks like this. So this is the angular distribution of the phase function. Polar plot of the probability, and you see the most likely direction is this one, right in the forward direction. But there is the first rainbow here, second rainbow there, and backscatter glory in this direction. So it can be anything. This is what the algorithm decided for the new direction. And now you have a complete scattering event. You jumped some distance and the scattering changed distance. And of course, we have multiple scattering, and you can get many of these events, especially in a cloud where the optical thickness, the average optical thickness is still 1, but the physical distance is very small between two jumps. So in a typical cloud, the jump width of the photon is something in the order of a few 10 meters. And you can imagine more scatterings means it becomes more expensive calculation. So that's the reason why the computational speed of the Monte Carlo model is related to the optical thickness. It's approximately proportional to the optical thickness. So if you have just a Rayleigh atmosphere, which is very thin, can be quite fast. If you add a cloud with an optical thickness of 100, let's say 100 times the Rayleigh optical thickness, your computational speed will go down by a factor of 100. Well, go up. Unfortunately, go down. It's bad for you. That's why I said go down. So you go on with the scattering until you hit the surface. It's probably one of the mountains we can see out there. No, it's actually not. It's my hometown. Again, the photon could be absorbed or scattered at the ground. So if it's scattered, you need to decide on a new direction. Yeah, probably not with the probability distribution for water, but you would use the probability distribution, the PRDF of rocks for the mountains, and then you choose a new direction. And on we go until something happens, until the photon is absorbed or leaves the domain at top of atmosphere. And the only thing left is counting. So you count all the photons at the ground, all the photons at specific height levels you're interested in. That's standard forward photon tracing, as straightforward as it is. My personal feeling was always everybody who is interested in multiple scattering should develop a Monte Carlo model at some point in time. And from that idea, we created a course for the students where they have 1 week to create a full Monte Carlo code with everything. One-dimensional. It's easier with just 1 dimension, but in 3 dimension, it's not much more difficult. But you can do most of the things in 1 week, and then you get a real good understanding how radiative transfer works, because you're much closer to the physics than you are with solution like two-stream or this sort or something like that. You get really a feeling of what's going on when you look at the photon path and the jump widths and everything. Good. So this is good old straightforward Monte Carlo tracing. There's different techniques. So I'm jumping over it since we have to save some time. When it comes to radiances, for instance, so I was just talking about the total number of photons reaching the ground. When it comes to radiances, things become more difficult. With a radiance, you're interested in photons in a certain direction. And here we have these receivers here who have some opening angle, but you see our photon number 2 doesn't hit the instrument under the right angle, so it doesn't contribute. This one contributes by accident, but most of the photons wouldn't contribute. So when you calculate radiances this way, by just waiting until a photon comes from the right direction, you would never finish. And you need quite some opening angle to get any photons at all. So there's many different techniques, so-called either local estimate techniques or variance reduction techniques, where you can actually force the photon to reach the detector under the right angle, like that's sketched here in this case. So that's the same sketch repeated again. It's the same photon path again. But what you can do is from each scattering event, you calculate the probability that the photon actually doesn't go here, but that it goes into the direction where your detector looks like. And same for this one, same for this scattering, same for this scattering. If you add all the contributions, you get estimate of the radiance. Well, when I say estimate, it's it's actually a calculation of the radiance. So this is no guess or approximation. You can show mathematically this is equivalent to what I described before, waiting until individual photons reach your detector by forcing them into the detector and applying some weight, because, well, it's maybe more likely or less likely than this direction here. So you have to weight the directional probability and everything, and you don't count one photon, but the weighted photon afterwards, then you can force many photons into your direction. Now, from a satellite perspective, well, if you turn the picture around and you're looking down, that's nice because the satellite has many pixels looking in nearly the same direction. So you would get a distribution. But most of you are LiDAR people. And for LiDAR people, life is much harder because you don't have LiDARs everywhere. You just have one. Well, you have two. You're in a lucky situation. You have more than one. So you could place them everywhere. So, but for a LiDAR, jump there. Problem is you have a location plus a direction, and here it becomes really hard. So in order to force photons into the LiDAR with multiple scattering, single scattering is easy because upward scattering, you get a contribution. But multiple scattering doesn't work because you're scattered out of your direction, and the next scattering is probably not into the cone again. It would be highly unlikely, but somewhere, and so you don't get any contributions. So you have to force your photon twice. So you have to force the photon to go into the beam and then the right direction. So it becomes more complicated, but everything is possible with Monte Carlo. But I jumped here. Yep. Mhm. Mhm. I can explain it here. Yeah, the question is how do we apply the weight? I mean, the weight for this photon arriving here is the probability of going here times the extinction along the path. Because you have a very different path, and you have to consider that the photon which is scattered in this direction might be extinct again. So here you have the extinction as a weight. And in principle, it works the same way when you force it in a different direction. You always have to consider the probability that it actually goes there, scattering phase function, and then the extinction along the way. Now, so we are abusing photons somewhere. They want to go somewhere else, but you press them, you urge them to do something that they don't mind. It just comes with extra computational cost for calculating the extinction here and so, but at the end, every photon contributes to the result, and not just once, but twice. If you have multiple scattering 100 times or so, this is quite nice. I just wanted to introduce this guy, Hermann von Helmholtz, so German physicist of the 19th century, and he was very, very important for Monte Carlo modeling. You probably didn't do any because now Monte Carlo modeling is 19th century. You need a fast computer for that, and the computer was yet to be invented 100 years later. But what he basically said, and it's very short statement here. Suppose, I don't read it, but he basically says you can trace light both ways, from the source to the receiver, or from the receiver to the source. So you can reverse the light path, can do backward Monte Carlo. And it's in fact very easy. It doesn't even matter if you have polarization or complicated stuff. It's always that the transmission, if you go from A to B, is the same as the transmission if you go from B to A. So you can reverse photon path, and this is very, very convenient when you have a detector located at a specific location, because when you start from the sun, the photons will go everywhere. And only few hit your detector. If you think of a pyrometer with an area of 5 square centimeters, there's no chance you hit it. Probably don't need that resolution. It doesn't matter if you calculate it 20 meters to the left or right. But when there's clouds, there might be a shadow 20 meters to the right. So might matter. Yeah. And if you do it backward, if you start from the detector and go towards the sun using this local estimate technique, then you can save a lot of computational time. So that's basically what I wanted to say. There's variance reduction techniques, various reduction techniques, which are very important. And it basically tells you when you use Monte Carlo, there's always different ways to solve a specific question. And this is very important to know. That's one of the reasons why you better ask us how to set up the model for your specific problem. Because, for instance, for thermal irradiance calculation, if you do it the wrong way, it takes a factor of 10 to the power of 6 longer. So we came up with something very quick, but still extremely accurate. No approximations, which is 6 orders of magnitude faster. But it's not prohibited to do it the other way around, because for some applications it might be useful. So different from this sort, where you just switch on this sort and everything is fine. Here you need to know if you better do it forward or backward or with ALICE or without ALICE or whatever. So there's choices to be made, and that's why we want to be involved. Good. And that's what I wanted to say. And we have to quickly switch over to Claudia, I think.